previous two sessions we talked about how the power is generated, we talked about how it's transmitted and then distributed, and now we're at the end point where the electricity is going to be used. So this session we're going to look at drawing a little circuit using some conventions and some symbols. I'm going to check your drawings, and then we're going to use those drawings to actually wire up that circuit. We're going to put a light bulb in it, and the light bulb's going to come on, hopefully. It's under 50 volts, we're allowed to do it. Those are the rules, pretty sure. Cool. So has anybody had any experience with any electrical circuits? No one's done any illegal electrical work?
When I was a kid at school,
Yeah.
in science, I think at school, we're just doing lights.
Yeah. That's all we're doing. Everything's plug and play. There's nothing really we can hurt ourselves with here.
We'll change the tube lights, put some ceiling fans in.
My father-in-law is shocking. I'm like, just let me come over. Anyway.
Electricity was pretty new in those days. We've got this new thing called electricity. Yeah.
So is any, no, that's, like I said, I use it as an example because a lot of kids in the class, students in the class, have their four-wheel drives with their setups and lights, and it's something we can sort of talk about as far as circuits that are allowed to have worked on by themselves. It's a bit of a thing. We've covered safety and housekeeping. For this, because we're doing something practical, we will just chuck our glasses on. We're all wearing boots, that's lovely. We'll chuck our glasses on just before we plug anything in, but that's fine. So, there are there's 3 that are required, 5 that usually go into making up a circuit. So we've got our power source, that's what's going to power our little circuit. What else do we think needs to be in our circuit?
Wires?
Yep, conductors, wires. So we're going to use banana leads for today. Conductors, so we've got our power source and we've got our conductors. What else needs to be in our circuit for it to
On and
do
off switch?
something? Yep, on and off switch. We call that one control. Otherwise it's just going to be on all the time, isn't it?
You've done this before.
No, because it's right in front of us. I see it.
Alright.
What about the thing that the switch operates?
Need something to operate.
Oh, the
And something to operate, right? We might not think about all these things all the time, but that's in every circuit that we would install, every circuit you guys would use. We've got a way to power it, a way for it to get around, some way to turn it on and off, whether that's a switch, whether that's a stop button, whether it's a start button, whether it's on a timer, whatever it is, it's going to have some way to turn it on and off, right? Otherwise, you just got a light that's on all the time. You're going to have some sort of protection. We're going to use circuit breakers. What would we have typically grown up with for some of the people in
Fuses.
the class? Fuses. They're still around, they exist. We sort of tend to move away from them these days. Can anyone think why that is?
Put a nail in it.
You can put whatever you like in it. Should you put whatever you like in it? Probably not, because what is the job of, what is the fuse's job?
Protects, I don't know.
Yeah, to protect the cable. And if it's not the weak point in the circuit, the cable's going to get damaged. And is it just going to gently snap and fall away? Do we
No,
think?
it'll
No,
catch fire.
it'll catch fire. And then what else will catch fire?
Whatever's around the cable.
Everything else around it. So, yeah, there's a slightly more modern, less.
It's safer as well to do it.
Yep, you're not out in the rain, in the dark, just trying to make something work, and the way you made it work was wrap it around 6 times. Yes, and you've got no lights obviously because the power's out, so you haven't got your torch and your fuse wire ready to go. Great, and then we actually want something in the circuit to turn it on and off, right? Otherwise, what's the point? You can have all these things in the circuit and it would work, but what's the point? We usually use resistors at this point in the class. Take some measurements and work out all our calculations, but you don't see anything actually turn on and off. So we're going to hopefully turn our light bulbs on and off. So we are going to have a look at some of our never worked document in these session plans before. So yeah. Okay, so I'm just going to use this part because it's nice and clear. So you can do it in a lot of different ways, the power source, and we're going to draw this together in a minute. We're going to put them in the right order, and I'm going to check everyone's. For this stage of the course and with these students, I would typically just do a little that's how I'm going to do my power source. Just it shows us everything we need to know. It's clear. We know whether it's AC or DC. We got the voltage. It's all there. We don't need a crazy little symbol. If it's a battery, you can do that. Then you still need to signify what voltage it is. What's another? If anyone can read any of those, what's another thing we're going to have in our circuit?
Circuit breaker.
Yep. So a circuit breaker and a switch are both really, really similar. So there's our switch. Now it's a circuit breaker. That's how we signify it in our drawings. So our switch is going to be very similar, but the X signifies that it's a circuit breaker. So we've got our power source. Our conductors are just straight line, nice and easy. Straight specifically. We don't draw our conductors like that. Depends what student you ask, I guess, sometimes, but that's typically how we do it. We're going to, aside from learning these symbols, we're also going to learn a few drawing conventions that we use as well for our plans. Does anyone know why we have conventions or rules with drawings? I'm sure you guys use them in your work as well.
So they're standardised.
Exactly. Like they're symbols, they're standardised. You draw things in certain ways so that other electricians or people can understand what it is that you're trying to signify in your drawing. And so one of the conventions we'll go over in a minute is we represent conductors with straight lines where possible. It's not one that the students are particularly good at, but that's okay, they get there. So we've got our protection, we've got our power source, we've got our control, and we've got our conductors. Our last one in this example is going to be a light. So we've got our conductor, comes down, and so that's our load. So I'm going to leave these up here. I'm going to swap over to our conventions, and we're just going to have I've already highlighted them for us to know which ones are going to apply for our little drawing, and then we're going to attempt to draw this. So that's our basic, what we need. These screens are orientated in a very funny way. Cool. So this isn't every drawing convention, but this is most of our rules to do with little simple drawing. So the ones I've already highlighted are the ones that are going to affect us for today. So once we've gone through a few of these, I'll turn the screen off and we will together attempt to put all of these components into a circuit. So what we've already covered is, I don't think anyone can read that from there, but all components are represented by symbols, preferably to Australian standards. So in our wiring rules, there's actually a page with symbols that are the most common. We wouldn't just put in a random thing that nobody else could understand, so we use Australian standard symbols. A big one is we draw all equipment and components in the unoperated condition, so when no current is flowing in the circuit. It's most important when they involve magnetic relays or contactors. It's still how we would like to draw our symbols and switches and circuit breakers, because it's not quite as obvious what's happening there compared to here. So we always draw our symbols in the unoperated condition. Generally, unless it doesn't make sense, and Tracy would have a much better idea about a lot of these because that's what she did, but we generally work from left to right and from top to bottom. Generally, the electrical supply is shown at the left or at the top, and not knowing some of these rules, you guys might just see them, but if you start to think, even in the video we just had on a minute ago, all those conventions were followed. And when we draw our circuit in a minute, they're gonna follow that. So if the supply is shown on the left and the sequence of operation is top to bottom, it's called a horizontal arrangement or a ladder diagram. If it's shown at the top, the supply is shown at the top, the sequence of operation is from left to right, and it's known as a vertical arrangement. Should have only highlighted half of that. Alright. There's one that, again, it won't affect us here, but generally the power circuit would be shown with a thicker line than the control circuit. It's another little one you can expand it out and see what parts of it are control and what are power. And then the last one we're going to pay attention to here is one I mentioned already. Conductors are represented by straight, vertical or horizontal lines wherever possible. Angled lines should only be used when unavoidable. So, bearing in mind those conventions, we're going to put these symbols into a drawing. We're all going to have a go at drawing it on our blank sheets of paper. I'll check them, and then we're all going to wire up our own little circuit. So, cool. So, bearing in mind all of those things, let's try and draw this fairly simple circuit on the board. Cool. So I'm going to start us off, and I'm going to do a little power supply over on the left, and we're going to use 24 volts AC as our actual supply. So we've got our 240 volts on the wall. Inside here is a transformer that will step this down to 24 volts, which is nice and safe for us to be using. So I'm going to use nice straight lines, come around. And so, can we remember what our protection is we're going to use for this circuit? Is circuit breaker. Cool.
That's the one with the X, yeah?
The one with the X. I've apprentices for 6 months that don't know that. Thank you. So we go through our circuit breaker first, like it would in our house. What's the next thing we're going to have in line? Yeah.
Switch.
We'll have our switch, makes sense. We want our switch before our anything else. And what are we actually going to turn on in our circuit? We're going to use some light globes and a lamp holder, or otherwise known as a load, but we would generally just be a circle with an X. And it won't work yet. But now it will. So we're going to use this, and then we've got our 5 components. We've got our power source, we've got our protection, we've got our control, we've got our load, and all linking them all up, we've got our conductors. So we've followed all of our conventions. We've used all our correct symbols. We've laid out a circuit that makes sense. So let me just quickly cast an eye over our drawing. Hopefully we've managed to copy that down. Wonderful. Excellent.
You need to switch out a circuit breaker. Just get by with just a circuit breaker.
You can use your circuit breaker as control.
I just don't, because I've got no idea.
No, that's fine. But
You're gonna
they essentially do the same thing,
Side to
right?
circuit breaker every time you want to turn the light on.
Oh, yeah. Yeah.
Circuit breaker will be outside in the switchboard,
But if we're
but
doing
your
something,
switch will be in your room.
Yeah.
but if we're doing something here, like testing light bulbs,
Well,
just use that.
think about how many actual protections there are coming in here. There'll be the main board, there'll be a subboard, there's a board in the room, which goes to the desks,
There's a box under the desk.
there's a box under the desk, there's a circuit breaker here. We're going to put a circuit breaker in, and then we got our light switch. So there's heaps of different points for it to be at, but a switch is going to be the most convenient
Oh,
thing for you. You can, but it's not generally advisable. Yeah, your switchboard might be 500 meters away from you,
yeah.
from what you're trying to turn on and off. Cool. Let's get cracking. So, it's true as well. And the circuit breaker, obviously, as part of its protection, there's a couple of things that will actually turn it off. So you could have a circuit breaker as your control, but you wouldn't have your switch as protection. Bill, I think. No.
Because they switch off automatically, isn't it? But it gets too high or something, voltage gets
Yeah, heat can affect it. It's one of the things. Let's just get Tracy to join one of these teams, unless we get one person to come over here, but it shouldn't. Please, I haven't got danger tags because we're only at 24 volts. I haven't had time to run through them. Let's not plug anything in until I go through it. So nothing plugged in over here. Let's also throw our safety glasses on. You can complain about it like all our apprentices.
This is weird.
And the last thing you guys are missing is we're going to use the single pole, so the one circuit breaker here as well.
This is our circuit breaker.
These are here. Ignore these. We're going to wire in our circuit breakers ourselves.
Somebody will line that, and then they'll work to that.
Yeah. So we're just using the single pole one for today.
Okay.
Ignore the three-phase one.
This one doesn't do anything?
That controls this box.
Oh, okay.
That's not our circuit breaker. We're putting it into our circuit, but this is our circuit breaker.
Should it be left on?
When we just leave it for now. Cool. That's all right. So we just need to. We'll start with a red cable going from our.
What did it?
What? Can't I just plug it in? Slow down. So let's go a red cable from our red plug on our transformer box. Red into the red. And then we'll go to the top of the circuit breaker. It actually doesn't matter for now, but into one of these parts. We always almost want to go through our devices. Sorry, Tracy, you can join one of these guys, or there's a station there. I just really think we might run out of cables, so do it as a partner. So that's our first step. So that's this cable sorted. We've gone into our circuit breaker. Now let's come out of our circuit breaker with another red cable into one side of our switch.
Does it matter what colour?
Look, it does. The cable itself, it actually doesn't matter to the cable.
Oh, okay. Just finishing the circuit.
I'm just going to finish it in a black cable just because it doesn't matter too much. For this, yep. Yeah, so
You trace it yourself.
yeah, right. Here you go. It's like you've done this before. Cool. So we should have our one cable coming out of our transformer into our circuit breaker, out of our single pole circuit breaker into our switch, out of our switch
See the load?
No, but
to the lamp holder, yep. And then we'll have a black cable coming out of our lamp holder to the black of the.
Hey,
It's a circuit.
I didn't lick my finger once.
Cool. So there.
now we've wrapped it with the stars. Why isn't it working?
Will it? Is it on?
Yeah, but I think does it work?
You could put your finger in there and see if it works.
Just get your tongue as far down into the. No, we would never. Alright. Yours also. I love checking single pass stuff when it gets to multi-pass stuff. Can I turn it on? You're like, just slow down. Give me a second. I can't instantaneously check everything you just done.
Piggybacks on the single part, like why? No, it's
Yeah. Cool. So, hopefully.
most of them
I'm gonna go.
don't back colours anymore, they keep everything's down ones.
Yes. Yeah, what can do?
Nah, nothing.
That's crazy. Why would that be?
The batteries are playing it.
Problem solved.
Yeah.
Why? It's flat.
So is everything on? Crazy. I think we're pretty good for everyone to plug their circuit in. Yep.
Ready?
Yeah. Oh.
Oh, that sounded good. Oh,
Oh. Advanced.
hey.
Alright. So obviously all of your protection's on. So this one's on, that one's on, and you're just controlling it with the light switch.
Oh, okay, red is good. Red is not bad.
Oh, red means on.
Red means on, not off.
Red means on. Yeah.
Green goes
Green
fast.
go.
Red goes faster.
Cool. So that's all of our circuits. We've been over. We've still got.
It's actually nice and warm.
My circuit breaker test.
It is nice and warm.
Could we put a second one in? Second light in?
We could absolutely chuck a second light in. Alright, let's turn those off for now. So Isaac said they're warm.
Oh no, it was just oh yes, it is.
Yeah, it's warm.
Yes.
Yeah, so we don't really tend to use. We'll wait a sec for the. Whoa. We'll unplug it before we.
Yeah, it is.
It is unplugged, great. Sorry. It's a bit different teaching people that aren't 16 years old. Cool. So yeah, you said it's hot. So remember before we talked about in the previous lesson resistance, and I said there'll be things that are designed to get really hot, and yeah, light bulbs one of them. So we don't tend to use incandescent light bulbs anymore because most of the energy is converted into heat. They make great heaters. The light output you get from them for how much wattage you put into them is very, very poor. So that's most of why we've moved across to LEDs. You put a lot less power in, you get a lot more light out. Almost none of it is lost to heat. So that's a big one. Super behind it, TAE, and we barely cover LEDs. Because why would you cover anything that's less than 20 years old? Cool. So over here we're going to put in a second light into our circuit, just on this side. We'll do 2 and then we can do 3 and 4, doesn't matter. We'll just see what works. Well, make that. Cool. Great, let's see what happens, whether the brightness is the same or whether... Oh,
Oh, no.
what's happened?
Hey, nay. You stuffed that up, mate.
So, we would say that the resistance has probably doubled in the circuit, right?
Yep. So
Yep.
why is one not brighter than the other? Because the resistance hasn't changed to the first one, maybe to the second one.
The current will be the same everywhere in a single pass circuit.
Oh, you mean like the hydraulic circuit, you mean?
It evens out, if you will. So that's what happens when you have twice as much resistance in the circuit. There would still be at 24 volts, but now 12 of it would be at each globe. If you can, I know it's a little bit hard to.
So if you've
you
got
can't see all this
half
stuff.
a dozen lights on in one circuit, does that mean you need to crank more power into it, or bigger wires, or what's the?
You're only going to have the same amount of voltage at home, 240.
The way you want it.
Yeah.
Oh, is it?
So this is a series circuit, and if I had another lesson, we would go into series versus parallel, and yeah, it's not something we have time for today. We only have 3 more minutes. Cool. Everyone built their circuit very well. We saw that it got less bright when we put a second light into it.
Didn't get as hot.
It also didn't get as hot. So yeah, like I said, the current's going to be the same anywhere in a single pass circuit, except now we know we've got 24 volts at the start. We could use one of Tracy's meters to confirm that, but we also now, that voltage is now cut in half when it gets to the light. It's a little bit hard to visualise all of this without testing it and backing it up, but that's what's happening. Cool, so we all plugged it in, we let the students turn it on. That's always a key step. Great, so yeah, the next thing we would get onto would be Ohm's law. If we had the time, we would do that. But just for now, I'm just going to very briefly look at how Ohm's law is represented. And we covered in that little video that we watched in between these sessions. So if we've got any 2 of these values as we go forward, and we could use this example to get all of these measurements and examples, if we had any 2 of these values, we can use it to find the third. So if we were to cover the value we're after, and here we've got current, here we've got resistance, voltage. If we had any 2 of these values, we could find the third. So if we needed to find voltage and we had current and resistance, we simply cover the voltage and we times our current value in amps. Here we've got our ohms, and here we've got our volts. So if we need to find voltage in our circuit, say we weren't given it, we just times our current value in amps by our